Good afternoon, everyone. Today we will discuss steel bridges. First, we will discuss the theory of steel bridges, and then we will discuss the design of steel bridges. So, let us start with this: the theory of the steel bridges. Main advantage of structural steel over other materials are its strength and ductility. So, why we are using the steel in bridges? Because of this requirement, that is the strength as well as the high ductility requirement of steel over other materials. So it has a higher strength to cost ratio in tension. Steel has higher strength to cost ratio in tension and a slightly lower strength to cost ratio in compression when compared to concrete structures. Okay. Now again, the stiffness to weight ratio of steel is much higher. If you consider the stiffness to weight ratio of steel, that will be much higher than that of concrete. Steel is more stiffer than that of concrete. Therefore, structural steel is an efficient and economic material in bridges. So because of these reasons, we are using steel in the long span bridges. Now, steel is indeed suitable for most span ranges, but particularly for longer span. For shorter spans, we are using some concrete bridges also, but it is particularly suitable for long span bridges. We are using the steel structures. Now, Howrah Bridge is also known as Rabindra Setu Bridge, is an early classical steel bridge in India. This bridge is situated in Calcutta. This is a continuous bridge. It was built in 1943 and it is 97-meter high and 705-meter long. Now, we have to classify the steel bridges. The classification is based on number one is the type of traffic which is carried on the bridges. Okay, which type of traffic is this? Whether it is railway traffic, whether it is a highway traffic, or the combined traffic. Second one, the type of main structural system. Whether the bridges supports a load by bending action or by arch action or some other action. Okay, that is the what is the type of main structural system. Third one is the position of the carriageway. Carriageway means where the load is moving. Okay, in case of uh, highway bridges, it is the road surface. In case of railway bridge, it is the railway line. So that is called your carriageway, where the traffic is moving relative to the main structural system. So we have to classify the bridges based on these three criteria. So let us first discuss classification based on type of traffic, which is carried by the bridge. So first one is bridges are classified as highway or the road bridges. If the traffic is highway, okay, or the road bridges, so we call it as highway or road bridges. Second is railway or rail bridges. And the third one is road come rail bridges. Both the traffics are there on one bridges. You will see one example of this one, road come rail bridges. When you are going towards uh, Old Delhi railway station, you will find a bridge in which both the traffics are running on it. So that is your road come rail bridge. Now classification based on the main structural system. So first one is your girder bridges. In case of girder bridges, flexural between the vertical supports is the main structural action. Okay, so we have a flexural action between the vertical supports of the columns. So that is your girder bridges. We call it as plate girder bridges. Now girder bridges will be either solid web girders. Okay, plate girders are all solid web girders generally, or box girders or truss girders. Okay, so we'll see that here. In case of this one, this is a two span plate girder bridge section. Okay, so we have a solid girder here, solid plate girder here. So that is solid web girder. Okay, this is the second example where we have provided the box girder bridge. Okay, so this is your box girder here, this one. And in the last, we have provided some types of trusses here. So that is called your truss girder bridge. So in this course, we will design a bridge based on truss girder type. Okay. Now, plate girder bridges are generally used for spans up to 250 meter. Okay. Plate girder bridge is only used up to 50 meter, and box girder is used up to 250 meter. Truss bridge, this type of bridge is used up to 375 meters. Now, the other type of bridge based on main structural system is your arch bridges. So the load transferred to the foundation by arches acting as the main structural element. So here the transfer of the load is by arch action. So we have in arch, we have axial compression in arch rib is the main force combined with some bending also. Okay. So these bridges are competitive in the range of 200 to 500 meters. So we know that this is my arch and here is my bridge. Okay. And this is another option, that the road or the rail surface is not at the highest point, which is here. It is in between the highest and the lowest point. It is here. So this is both are your arch bridges. Then we have cable stayed bridges. Now in case of cable stayed bridges, as you see in this picture, cables in the vertical planes support the main longitudinal girder. So this is my longitudinal girder. We have provided the towers at these locations. Okay. And the cables in the vertical planes support this main girder. So these cables are attached to the main girder here at several locations here, and in this way the longitudinal girder is supported through the help of these cables. Okay. So these cable stayed bridges are economical when the span is about up to 150 to 700 meters. Then we have the suspension bridges. So in case of suspension bridges, the bridge deck is suspended from cables. So this is my bridge deck and it is suspended with the help of these suspenders, okay, from cables. So this is my cable. This is my cable which is passed over these two towers here. Okay, we have a pulley here and we have a mechanism to anchor these cables here and here. Okay, so this is called your suspension bridge. Okay. Now, currently, the suspension bridges is the best solution for long span bridges. Among the various solutions which we have discussed previously, this is the best solution for long span bridges. Now, next comes the classification based on position of carriageway, where our traffic moves. Okay, so basically, the first classification is called deck type bridge. In the deck type bridge, the road or the railway line or the traffic is passed at the top chord level. So this is my truss here. This is bottom chord members here. This is top chord members here. So if the load is passing over the top chord members, or you can say that the road surface or the railway line passes over the top chord member, then we call it as deck type bridge. Okay. Then we have through type bridge, second classification. In through type bridge, the road or the railway line is passes over the bottom chord members. So here it is, the road or rail surface is here. So the load is passing at this level. Okay. So this is your through type bridge. Then the bracing of the top flange, when the load is passing here, okay, the train is moving here. So we have to provide some support at the top level. So we have to provide for that the bracing at the top flange or the lateral support of the top chord under compression is also required. So you'll see there, this is my bottom chord member. This is my top chord member. Okay, the train is moving or the road is here at this level at the bottom chord. Okay, so we have to provide some mechanism for lateral support at the top. So we have to provide this cross bracings here. These are the cross bracings here. So this is your bracing at the top flange or the lateral support of the top chord under compression. This is mandatory or it is required. Okay, we will discuss this sketch further in detail after a few slides. Okay. Now next is a semi-through type of bridge. In semi-through, the carriageway is neither passing here at the top chord level nor here at the bottom level, but it is in between here. Okay, so this is called your semi-through type of bridge. The bracing of the top flange or the top chord under compression is not done. So in this type of bridge, the bracing at the top chord members, which I just showed you in the previous slide, is not required. Okay. Now let us discuss the geometry of the truss bridges. Okay. So you will see that let us starting from here. This is my abutment, bridge abutment here. This one. Okay. And here it is your bearing here. So one support is here. So we have to provide a bearing here. Now this member here, this one, this is called your bottom chord member. Okay. So one member is bottom chord here. The other member is this one here. Okay. So this is my bottom chord member. Similarly, the member which is here and the member which is here, this is called your top chord. Okay. Now we have some vertical members also. This is my vertical member, vertical member. This is also vertical, vertical. And these are your diagonal members. So this is my diagonal member. Okay. This is my diagonal member. Okay. And in the center, we have to provide full diagonals in both the directions. Okay. So let us come to next here. We said this is my bottom chord member here. Okay. Now this bottom chord and this bottom chord, it is joined by these beams. These beams. So these beams are called your floor beams. Okay. Now these beams, over these beams, we have to support these longitudinal members. This one is here, the other one is this one, longitudinal members. So these longitudinal beams are called your stringers. Okay. Then over these stringers, we have to provide the here we provide the railway sleepers in this direction. Okay, over it at regular interval. Then over the sleepers, we have to provide the railway line. Clear? Now, in the last portion of the bridge, we have to provide this inclined post where the bridge ends. Okay, so this is called your inclined post. And we have some provide a special type of bracing is here, which we'll discuss later on. What is this one? Okay, so this is just provided in the last panel, or you can say that in the inclined post here. Okay, so let us again just discuss this one. This is my bottom chord member. Okay, this is my top chord member. Okay, these are my bracing at the top chord level. Clear? This is my vertical here. This is my diagonal member here. Okay, this is my floor beams. So floor beams are resting on lower chord members here. Then over floor beams, we have to provide stringers. These are my stringers over the floor beams. Then over the stringers, I have to provide sleepers at regular intervals. Then over the sleepers, I have to provide my railway line or railway track. Okay. So in this way, this is the some can say that the geometry of this truss girder bridge. Okay. Now this is one section here. Okay. You will see that the section of the previous one. You will see that here this is my lower chord member. This is my lower chord member. This is my top chord member. This is my top chord member. Okay. And this one, this rectangle from here to here. Okay. This is my floor beam. Clear? Over the floor beam, I have to provide this is my stringer here. This is my stringer here in the cross section. Then over the stringer, I have to provide a deck if it is a highway bridge, or I have to provide sleepers here if it is a railway bridge. So this is my deck, this is my curve, and this is my railing. Okay. Because such type of bridges are required regular inspection, so I have to provide a cross bracing here. Okay, from top chord to the bottom chord. So this is called your sway bracing diagram, sway bracing. Then on this sway bracing, I have to provide at this level a platform, okay, which is called your inspection volume. So for inspecting the health of this bridge, okay, we have to use this platform. So this platform runs continuously throughout the bridge. It is called inspection galley or inspection walkway. Okay. Now, this is another section of the bridge. You will see that this is my elevation. This is my bottom chord member, this one. This is my top chord member. Okay. This is my vertical. This is my diagonal member here. This is my diagonal member. This is my end member or end post. Okay, this is my end post here. Now suppose that if I just see the plan at AA, see the plan at AA. So this is my section AA here. Okay, I have see the plan here. So here in this plan you see that this is my bottom chord member, one bottom chord here. Okay, this is my floor beam here. Okay, then we have these are the my stringers here. Okay, this is my cross bracings. So this cross bracings is also provided at the bottom chord member also. Okay, so this is my cross bracings. Now if you see the plan at the section BB, so my BB section is at the top here. So we have, this is my top chord member, this is my top chord member, and we have these connection between the top chord member, and we have these cross bracings to resist the lateral force. Okay, so this is called your top laterals. Now we have the section CC here. Okay, CC is the section just before the last panel. So this is my last panel, this is the just last panel, CC here. So we have to provide a special type of bracing that is called your sway bracing. Okay, so this is my sway bracing, only provided here only. Okay, just before the last panel, so here as well as here. And in the last here, where this is my inclined member here, we have provided a special type of bracing that is called your portal bracing. So this is your portal bracing, only provided here, here as well as here. Okay. Now come to the what are the various types of loads on the bridges. So the first load is dead load. We have to consider live load is we have to consider impact load, longitudinal force. We will discuss one by one in detail. Thermal force, we have wind force, seismic force, raking force, force due to curvature, forces on parapets, friction resistance of expansion bearings, erection forces. Okay, so these are some of the various forces. We will discuss one by one. Now first is the dead load. Dead load is the weight of the structure or any permanent fixture on the bridge. It is initially assumed, okay, and checked after the design is completed. Live load. Bridge design standards specify the design loads. We are using some design standards for the live loads, okay, that are called bridge design standards. I will show you a sample of bridge design standard after one slide, okay, where the design live loads will given to you, okay, permitted to pass over the bridge. Okay. Now we have the railway bridges. Railway bridges are to be designed for railway standard loading. Now we have different types of loading. For highway bridges, the loading are different. For railway bridges, we are using standard railway loadings given in bridge rules. Okay, I will show you. Okay, the standard of the loadings are. So we have the broad gauge line. Okay, in again broad gauge line, we have the main line where most of the traffic passes, and we have direct branch line where only few trains are passing in a day. Okay, so we have main line as well as the branch line. Similarly, we have meter gauge also. We have main line, branch line, and we have standard C also. Narrow gauge also we are providing in hilly areas. H class, we have three types of classes: H class, A class, main line, and B class, branch line. Okay. Now what is this? The actual standard loads have been expressed in bridge rules. So the live loads are given in the bridge rules as equivalent uniformly distributed loads. EUDL. We call it as equivalent uniformly distributed loads in tables to simplify the analysis. So this is one such table, okay, for EUDL. You will see here, this is first column is your L, that is span in meters. Okay, then second is your total load for bending moment in kilonewton. We have two columns here. ML means main line, BL means branch line. So if you have designed a bridge for main line, to use these values, is for the branch line, use these values. Okay, similarly total load for shear force in kilonewton, this is for main line, this is for branch line. Okay, and in the last we have the impact factor. The formula for impact factor is given as 20 divided by 40 plus L. What is L? L is your span in meters. Okay, we will discuss later on what is the meaning of this impact factor. So corresponding to each span meter, we have an impact factor here. Okay, we will discuss later on. So this is how the loads are calculated with the help of bridge tools, design tables. Now these UDL values depend upon the span length. As I told you, these are depend upon the span length. So you see that as the span is increasing here, okay, the load is also increasing here. Okay. EUDL for bending moment and the shear force for broad gauge main line loading can be obtained by the following formula. So how these loads are calculated? So these are calculated by the following formula. For bending moment, EUDL is equal to 317.97 plus this much quantity times L. L is the span. Okay, this span is meter plus 0.0188 L square. Okay, so this load should always be greater or equal to 449.2 kN for bending moment. So whatever the span you have of your bridge, just put the value here and here, you will get the EUDL. Okay, or just use the ready-made tables for the design. Okay, for taking the load for bending moment as well as for the shear force. Okay, for shear force, this is the formula. Clear? Now L is the effective span for the bending moment and the loaded length for the maximum effect in the member under consideration for shear. For L is the effective span for bending moment. Okay, and L is nothing but the loaded length for shear force. When you are calculating this for shear force, L is not the span, but it is the loaded length. Okay, suppose that a train is passing over the bridge and it is partially passed over the bridge. Some train is on the back side of the bridge and some on the bridge. So we'll consider only that part of the load of the train which is on the bridge. So it is nothing but the loaded length for the maximum effect in the member under consideration for shear force. Yes. Now come to the impact load. Now, impact load means dynamic effect caused due to vertical oscillation. When train is passing over the track, there will be vertical oscillations are there. So when oscillations are there, so we have a dynamic or the impact type of load is there. So we have to account for that load. And periodical shifting of the live load from one wheel to another. And when train is moving over the bridge, okay, so the live load is passes from one wheel to the another wheel. Okay. So this means that this load is continuously changing. So because it is varying with time, that's why it is called your dynamic effect or the dynamic load or the impact load. Okay. This dynamic effect of the moving load is taken care of by increasing the live load by a factor called impact factor. So you have to increase the live load by a factor that is called your impact factor. So I will show you how to calculate this impact factor here. You will see I just show you this table before in the previous slide. Okay, this is the same table. So we have this impact factor here. This is the formula for impact factor. Okay, so just put the value L here. You will get the impact factor. So whatever the live load you are getting from here, just increase the live load by this much factor. Okay, to account for dynamic effect or the impact load of the vibration on the bridge due to movement of the train. Clear? So first is your dead load, second is your live load, third one is your impact load. Impact load, you have to calculate the impact factor from here, okay, and just increase the live load by this impact factor to account for the dynamic effect. Third one is your longitudinal force. Now, why this force is acting here? So longitudinal force are set up between the vehicle and the bridge deck when the former accelerate or brake. When the train accelerate or brake on the bridge, okay, so we are getting this type of force that is called your longitudinal force, and it is given by this formula. W is the weight of the vehicle, okay, G is acceleration due to gravity, and del V over del T is nothing but the change in velocity in time delta T. When it is accelerate, so we have del V over del T, or when it is brake, we have del V over del T, which is different here, okay. So with the help of this formula, we have to calculate the longitudinal force and duly incorporated in the design. Now, when there is a longitudinal force, this means that when the train accelerate or apply in the brake, so we have to provide a special type of bracing on the track to account for this acceleration or braking of the train. So what we'll do here, this is my stringer here. I already explained to you. This is my stringer. This is my cross bracing. So if it is a single track bridge, So what we will do? We have to provide this strut here and strut here. Okay, between stringer to stringer. Okay, so this strut is accounting the longitudinal force. So we have to provide this strut here, strut here, strut here. Okay, for single track bridge. Now suppose that if it is a double track bridge, so what I will do here? Okay, we have to provide this cross bracings. Okay, as it is. So we'll see that this is my you can say that this is the center line of the bridge here. Okay, this is the center line of the bridge. Clear? One string the for this right side of the this center line, we have one stringer here, one stringer here, and this is my center line of the track. Similarly, on the other side here, this is my stringer, this is my stringer, and this is my center line of the bridge. Okay, so I have to provide the uh, stringers here as usual practice. Okay, but in the last here, when the bridge ends here, so we did not provide such type of struts. When it is double track bridge, we have to provide this type of truss, which is called your traction truss. Okay, so this traction truss you have to provide it between here. This is my stringer for one track, one stringer here, one stringer here. Okay, this is my stringer, so we have to provide a diagonal here. Okay, this is my center line of the bridge. Okay, this is my stringer here, this is my stringer here. I have to provide a cross truss here, and similarly on this side you have to provide a diagonal truss here. So this truss is called your traction truss. It is provided in double track bridges. Now come to the wind load. Wind load may be act horizontally, means transverse to the direction of the span, means we can say that the, in the direction in the perpendicular direction of the movement of the train, that is called your transverse load. Okay, wind load, that is acting in the transverse direction. It is also acting in the longitudinal direction along the direction of the span, which is small as compared to this one. And third one is also upward or uplift force. Okay, on the track. Wind load is generally not significant in short span bridges. It is only significant in the long spans. So for the purpose of the design, wind loadings are adopted from maps and tables given IS 875 part 3. Okay, for wind load, just consult this code. Next is the force due to curvature. Now sometimes we have curvature on the bridges also. We have curves. Okay, so when there is a curve, so allowance for centrifugal action of the moving load should be made in the design by member. So when there is a curve is there, so we have centrifugal action. Okay, so to counter this centrifugal action, we have to provide some allowance. So what is this? All the tracks and the lanes on the structure being considered are assumed as occupied by the moving load. So here we are considering that all the lanes on the bridge are occupied by the load. Means total train on the bridge, not partially. Okay, when we consider the force due to curvature. This force is given by this formula, WV squared divided by 12.7 R. Okay, C is the centrifugal force in kilonewton per meter. W is equivalent distributed live load. We have already calculated from the table. Okay, V is the maximum speed of the train in kilometers per hour, and R is the radius of curvature in meter. Okay, so using this, we have to calculate C. Next is your raking force. What is raking? This is a lateral force produced due to lateral movement of rolling stocks in railway bridges. When train moves at a high speed, you will notice that it is you can say that there is a slight lateral movement of the train. You can say the bogies also lateral movement, lateral vibrations you will feel when the train is moving at a faster speed. So that is called your raking force. Okay. So this, for this, to account for this raking force, what you will do, you have to provide lateral bracing of the loaded deck of railway spans. So you have to provide lateral bracing at top and bottom. As I told you in the slide before, when we discussed the components of the bridges, we have to provide the lateral bracing at the top and well as the bottom of the railway spans shall be designed to resist, in addition to the wind and centrifugal loads, a lateral load due to raking force of, we have to consider this lateral load as 6 kN per meter, treated as moving load. So we have to add this moving load in the live load. Okay, we consider it as a moving load. So in this way, we have to consider this raking force. This load is considered only in computing loads in the lateral braces. Now come to the seismic load. Now, if the bridge is situated in earthquake-prone region, the seismic forces are given due consideration. So earthquake cause either there is a horizontal motion or the vertical forces are there in the structure that will be proportional to the weight of the structure. Okay, so both horizontal and the vertical components have to be taken into account for the design of bridges. Okay, so for this we have to consider this code IS 18993. This code is revised. Okay, you will consider this as 2016. Okay, this is the old version of the code. 2016 may be referred to for the actual design codes. Next, come to the load combinations. So we are generally taking 4 load combinations are generally considered important for checking the adequacy of the bridge design. So what is this? Number 1, we have stresses due to normal loads. So we will consider dead load, live load, and impact load as well as centrifugal force. Generally, we consider these 3 loads: dead, live, and impact. If this force is small, we will neglect it. Okay, for the normal conditions. So in the design, we will consider these 3 loads only: dead, live, and the impact load. Second is the stresses due to normal loads plus occasional loads. Occasional means we have to consider either wind load or other latent loads like longitudinal or temperature stress. Okay. Third one is the stresses due to loads during erection. Okay. So load combination means we are just considering this one. And the last one is stresses due to normal loads plus occasional loads. Okay. Plus extraordinary loads like seismic load. Okay. Excluding wind load. So when we know that when we consider the seismic load, we exclude the wind load. So what we'll do here, we will consider the loads as in 2. 2 means this one, that is normal load plus occasional load. Occasional means wind. So normal loads as in 2 plus seismic load instead of wind load. So you have to consider seismic load instead of wind load. So these are also given in table 7.2 and also specified in IS 1915 1961. Okay. So this is all about the theory of the steel bridges. Okay. So in the next lecture, we will discuss the design of steel bridges. Thank you very much.